Again, this is going to be the continuation of from the introduction of the double integral and Fubini's theorem, and then you may find the other proof, and this video will be independent, pretty much independent from the other proof, but it still relies on introduction part. So I want you to watch the introduction video first to make sense out of this, but there will be one lemma that I will refer to the proof part 1, but this largely is independent. So let me remind you of the Fubini's theorem, that the way it's introduced there. And this is the rectangular region we're looking at, and these are the two iterated integral. It doesn't have to be the volume of anything, it's just a repeated integral. As long as it makes sense, it's just two objects. Fubini's theorem, it says these two things are equal to each other. So the main difference here is fxy and fxy. Integrated y first, x first here, then x later, and y later. These two iterated integral in a different order is actually equal to each other. Just like the Clairaut's theorem, differentiated in a different order equal to each other. And I think I explained in the part 1 of the proof that about this one, but we don't need that in here. So the main thing we're going to do is that in this part of the video, we're going to actually make a connection to this one, this iterated integral, to this double integral, right? So we show actually that this particular iterated integral is actually equal to this double integral. Okay? Then from there, that construction doesn't really rely upon which direction we're into doing the iterated integral first. Therefore, it nicely construct this equality there. So the main part is the following, as I explained in the introduction part, that this way of looking at the volume right here is kind of introduced in a Calc 2. This is called a cross-sectional method. You strip up a solid into a sliced cross sections and defining the volume in that way. The key word is defining. We're not approximating, we're defining the volume in that way. And here in Calc 3, we're defining the volume using this idea of a double integral. So this main thing about this part is that connecting this definition, cross-section definition of the volume, and this double integral definition of the volume, we're showing these two things are equal to each other. Then this is another cross-section, therefore these are all equal to each other in establishing this equality there. And in general, the Fubini's theorem is stated for continuous functions, but that involves a lot of topological techniques and tools, especially compactness and an equicontinuous property. So we limit ourselves to the class of function that have continuous partials. In that way, you can use mean value theorem and proves things like this rigorously with a calculus first year and second year calculus flavor in it. So that's our goal. So let's look at this object again. And we're relying on the introduction part of the video that kind of defines all this thing. But here's the theorem. If we consider that class of function continuous or function with a continuous partial, this double integral exists. What that means is that if you partition that rectangular region R, and however you do it irregularly, and it's going to create a lot of different shape of rectangles, and from each piece of rectangle, if you choose arbitrary sample points of each of a rectangle indexed by kj like this, and if you compute this sum, which represents the sum of the volumes of that tiny building, as I said, and this approach is a common number, and no matter and however and whenever we partition this thing, as long as it's getting refined enough, it's going to be always going to a same number all the time. If that's true, and we say this exists, so we have this property. This is the part where I refer to the lemma 1 of the proof part 1 in there, is that these two functions exist. And that's the difference, double integral, and this is iterated integral. And what we do there, we recognize this inside as a function of x, because to do this iterated integral, inside part of the integral, we treat x as some given constant and do the integral, right? So we can look at this as a function of x, and to show the outer integral exists, we want to have a condition that inside, as a function of x, is continuous. So that's the lemma part, and here is the same. If you look at this as a function of y, because we're integrating with respect to x, then outside integral requires this thing to be continuous to guarantee the existence. So here's the lemma, and if gxy has continuous partial, again the result holds for continuous function, but we are limiting ourselves into this class, then x is in there treated as a constant while we are integrating. For each such x value, this is going to be some value, so it's a function of x. Then as x approaches x0, this is actually the integral with that x0 value in it. So if you think about the definition of a continuity of one variable function, this is exactly the definition of the continuity of that function. So we prove that this inner integral as a function of x or y here, they're a continuous function, and therefore both outer integrals exist. And we should never neglect, when you think carefully, the existence of something. This is an interesting part, and this is the main motivation that we decided to actually present this here. So let's look at this, and g is a continuous function, and we have a partition of this interval from a to b. So it's not uniform partition, just an irregular partition. Then I'm claiming that from xk star from each of this interval, and such that if you compute this type of the Riemann sum, it's going to be equal to this integral. It's not that it's approaching this integral. It's going to be exactly equal to this interval. And in particular, you don't have to chop it out to anything. You just keep it, this whole thing as one chunk, a to b, and the n is 1 here, n is 1. And then there will be in gk x star just one value here, since n is 1. It's going to equal this integral value. This is actually the mean value theorem if you think of it that way. But mean value theorem applied to this each of the interval will be this result. Let's take a look at the proof. And the most important part here is it's equal. Equality is important. And so now I wrote it up here, and we're going to prove it. Here first we have for each interval, the kth interval from xk minus 1 to xk. Because it's a continuous function, we always have, for all this interval, some point where the function takes a maximum, and some point here, let's say xk hat, tilde, the function takes a minimum value. So mk for the maximum of kth interval, little mk for the minimum of the kth interval, as written here. So we have the following inequality. If you actually integrate this gx over this tiny interval, this is the upper and lower limit, and we have following inequality. This gxk hat here is a maximum value, and multiplied by this width, which is delta xk, will be obviously the area of the rectangle, which is, because we use the highest point, that must be bigger than the actual integral value. And similar for this one, because we use the lowest point right there, and this area of the rectangle must be smaller. And this still holds when mk or mk, big mk and little mk are negative or positive, however. So that needs to be checked, but we have this result. So let me write it up there. So organize it this way. So interesting part is the following. This quantity here is fixed, and km for xk minus 1 and xk. And then there is this choice of xk tilde and xk hat, and delta xk is fixed. Because g is a continuous function, by something called intermediate value theorem, or just intuitive notion of continuity, as we vary this xk tilde to xk hat, one way or another, you should be able to continuously change this value of g from here to there, right? Then, using this intermediate value theorem, we have the following. Intermediate value theorem says if you go from one value to another value continuously, it must hit whatever the intermediate value is. If you pull up the statement of the intermediate value theorem, that's basically what it says. G varies continuously, it must hit all the intermediate values. Alright, the intermediate value is the integral over this kth interval, and that must be evaluated by this form of shape, a gxk star times delta xk. So that's exactly equal. So if you use, instead of xk minus 1 xk, if I just use a to b, there will be such a thing there. Instead of delta xk, there will be b minus a. Then that is the integral version of the mean value theorem. But for each interval like this, we have this statement, which is basically it for the proof. So I wrote it here. Each of this entire integral is the sum of an integral like this. Therefore, each of this n integral split is written like this. Therefore, these two things are exactly equal to each other for some special values of xk star. Alright, I think we're ready to prove this statement. Iterated integral is actually a double integral. Okay? And we're going to call this inside function of this iterated integral gx. Again, this is a function of x, so it's going to be gx. Now, by the lemma 1, which is from the proof part 1 video, g is the continuous function. Then, to make a connection to the double integral, we're going to consider partitions. So we're going to have this arbitrary partition, xk minus 1 xk, and yj minus 1 yk. We have this partition along the x side and y side, and it has these n values a, b, c, d. And we rewrote this iterated integral simply like this, a to b, and inside we call it gx. And it was just a minute ago, it was shown that in each of these integral, as long as gx is continuous function, right, then we can write it. This is our interval, and exactly this equal is not approaching exactly equal to the sum of this Riemann sum shape by lemma 2, which we call lemma 2. So let me summarize it up here. This iterated integral is written in an exact way, somewhat integral version of the mean value theorem again kicks in, wrote an exact Riemann sum value. Then here we write g, by definition it was integral in dy, so plugging an xk star in there, and this is a y integral. The key thing is that we're looking at this function just like gx, gy, or gx before. This is a function of y, and every time if you have a different xk star value, it's going to be a different function of y. So this basically we're looking at n different functions inside here, and we're integrating from c to d. So here's the situation. xk minus 1 is here, and xk is over here, and xk star somewhere in between, some special values. And along that part, we have this choice of a y value is going to be made. For each of this k star, xk star, this one, the lemma 2 applies again. Again, let me say that again. For each of this k, there is this value xk star, the lemma 2 applies again. Lemma 2 says that this integral can be rewritten as an exact sum like this. So by lemma 2 we have this one. For given k, depending on xk star, this this function inside is rewritten as a Riemann sum from j to j1 to m, the given interval here, however you split it up. There's no dependence on how we split it. This is our free choice. You can always split it up into however you want. M pieces, for example. For each of this y interval here and there and here and there will be a choice of points like this. And then if you go to the different column here, it's going to be the different choice of points there. So the kj is the correct index for that. For each k, there will be a different jth y value such that this integral value here is exactly equal. And this sum is exactly equal to this value of integral. Now if you look at this delta yj times delta xk, that's exactly area of this tiny piece right there, so we can rewrite it as a delta akj. Once you write it, it looks just like the Riemann sum of that one. Okay, Riemann sum for the double integral. And the magic is that this double iterated integral here is exactly equal to some special Riemann sum like this. And another part, it's difficult part at this stage might be difficult to comprehend, is that this type of Riemann sum, because this one exists, that's the theorem was set out, because this one exists, however you chop this one down, this one's supposed to approach this value right there. So I summarize it over here. These are the kind of choices of xk star involved in here and ykj involved in there. And this is a crazy part, is that this part here is a constant. When we look at these two parts, this one approaches that one, it seems like this one is changing, and it is, supposed to getting arbitrarily close to this value, double integral value. But the fact is that this one never changes. This is some value, and this Riemann sum in this form is as if it's going to change, but it's always like that. No matter how you chop it down, there is a special values always equal to this double iterated integral. So this approaching is kind of trivial. This is a constant, supposed to approach that value, had no choice. This must be actually called that. It's kind of weird argument, but it's absolutely true. Therefore we proved not only this one approaches that because it doesn't change, this is this value. Well, in this argument there's nothing special about doing x first or y later. The main connection is that as long as we look at the sectional method is the same, cross-section method of computing the volume, defining the volume, not computing, is equivalent to defining the volume with a double integral, then the other cross-section is going to be obviously the same. So let me summarize it here. We're done, believe it or not, that we established the equivalence of the definition of the volume of a cross-section with a volume using double integral. Therefore, we have proved the Fubini's theorem like this. Okay? But in the proof part 1, we actually look at these two objects with just an integral problem and try to approach it from there using the derivative technique. But once you connect it to this double integral idea, and this kind of also connects to why these two things are equal to each other. And this technique, and I've shown in this video, is not limited to something we can see. The double integral can be defined in however you want. If you think about the definition, it doesn't depend on our visualization. So Fubini's theorem of this type can be still, for the 3 or more variable, can be still proven using this idea. Alright, thanks for watching. It was a long video, but I think it's worth thinking about this type of thing.